Good morning, everybody. We have started the chemical energetics, and last thing we had seen the different thermodynamic processes. The processes like isothermal process, adiabatic process, reversible process, irreversible process, isochoric processes, isobaric processes, and then we had started with the heat of formation of the substances. So, in that we had seen the definition, the standard heat of formation of the substances, and also we had seen the significance of this heat of formation. We have seen that from the values of heat of formation of the substances, we can calculate the standard heat of formation or of the substances, as well as the heat of reaction can also be calculated from the values of heat of formation of the substances. Now let's go further. The standard heat of combustion. Now the combustion is nothing but the process of complete oxidation or a process of complete burning a substance, that is nothing but the combustion. Therefore, what is standard heat of combustion? The standard heat of combustion is nothing but the amount of heat either evolved or absorbed when 1 mole of any substance is burned completely into the product at the standard conditions of temperature and pressure, that is called as the standard heat of combustion. That means at 298.15 Kelvin temperature and a pressure of 1 atmosphere, when a substance, 1 mole of any substance is burnt completely into the product, that heat, the amount of heat which is evolved or absorbed, that is called as the standard heat of combustion. And we can take one example. The combustion of methane, which is carbon dioxide and water. Now for this reaction, the standard heat of combustion, that is delta H0C or delta H0 combustion, it is denoted as, and this heat is minus 890.4 kilojoules. Now the heat of combustion, we had said that this combustion takes place at standard condition. That means the temperature is 298.15 kilojoules and the pressure is 1 atmosphere. This doesn't mean that combustion occurs at 298.5 Kelvin. Obviously, to do the combustion, we have to increase the temperature. The temperature in the combustion reactions are much higher than this temperature. That means what this condition means? The temperature is 298.15. That means that the reactant and the product are at this temperature. This doesn't mean that the reaction takes place at this temperature. The reaction takes place at higher temperature than this. So the standard condition of 298.15 Kelvin temperature means the reactant is at this temperature, but during the reaction the temperature may increase. So this is the standard heat of a combustion, which is denoted by delta H0C, and this is a combustion reaction here. Now the next, that is heat of neutralization. Heat of neutralization. Now we know what is the neutralization reaction. The neutralization reaction is nothing but when an acid and a base react to form the salt and the water, that simply we call it as the neutralization reaction. And the amount of heat change, whether it is evolved or absorbed in this reaction, that is called as the heat of neutralization. So the definition is made such that the amount of heat change when 1 gram equivalent of acid reacts with 1 gram equivalent of base, the amount of heat change that is called as the heat of neutralization for the reaction. So generally, actually, this heat of neutralization, it is calculated in the dilute solutions of the acids and the bases. This is because in a dilute solution, the dissociation takes place to the greater extent. That's why to measure the heat of neutralization, the acid and the bases are taken in their dilute solution forms. So, if we consider the neutralization of the hydrochloric acid with the strong base, that is the sodium hydroxide, we know that these both HCl, that means the hydrochloric acid, is also strong and NaOH is a strong base. So when such a reaction takes place, there is a formation of sodium chloride and water. Now if we take 1 gram equivalent of acid, 1 gram equivalent of base, obviously 1 gram equivalent of the product will be formed here. Now in such type of the reactions, these both are the strong electrolytes. Hence, in their dilute solution, they dissociate completely. Therefore, all the H plus ions from the acid reacts with OH minus ions of the base and they form the water. Here, always the heat of neutralization, it is always equal to 57.1 kilojoule for a reaction between 1 gram equivalent of any strong acid and 1 gram equivalent of any strong base. The heat of reaction is always minus 57.1 kilojoule. Now, as we know that as these both are strong electrolytes, so in aqueous solution, both of them dissociates completely. So if we write this reaction in the ionic form, this can be written as H plus Cl minus plus. This will dissociate as Na plus plus OH minus, which will give, this will also form the ions, that is Na plus and Cl minus, but the water will be undissociated. Therefore, if we cancel the same ions on both the sides, therefore what we will get? The reaction, that is only H plus plus OH minus gives water. So therefore, the heat of neutralization can also be defined as the heat change when the H plus from acid and the OH minus from base reacts to form the water. That is also the heat of neutralization. So here the H plus and OH minus ions combine and form the undissociated water here. But this amount of heat which is evolved, that we have written, that is in case of only strong acids and the bases. Strong acid like hydrochloric acid, nitric acid, sulfuric acid, and the strong bases like sodium hydroxide, then potassium hydroxide. When such strong electrolytes they react, therefore this much amount of the heat is released here in the reaction. But if the acid, if we consider it is a weak acid and the base is a strong NaOH. In this reaction between an acetic acid and the sodium hydroxide, here the acetic acid is a weak electrolyte or weak acid it is. So amount of heat which is released is not exactly minus 57.1 kilojoule. It is less than that. So why it is so, that we are going to see. So acetic acid, we know that it dissociates weakly as acetate ion and H plus ion. This is what is the dissociation reaction. Even in the dilute solution, the acetic acid dissociates like this. While NaOH, as it is a strong base, strong electrolyte, so it will dissociate as Na plus plus OH minus. And as we have seen here, the heat of neutralization, here the H plus from acid and OH minus combination takes place, and then the water is formed and the salt is formed. So in this reaction, the reaction between this H plus and OH minus proceeds to form the undissociated water. Now, the acid which we have taken is a weak acid. So, the amount of heat which is released during the combination of H plus and OH minus ion some of the heat is used to shift the equilibrium of the first reaction towards the right. See what I am telling you again. Here, during the combination of H plus ion which are formed from the dissociation of the acetic acid, these two will combine in the neutralization reaction. So during the combination or the reaction between H plus and OH minus ion, the amount of heat which is evolved, that is again same, but some of the heat is used to shift the equilibrium of first reaction towards the right. Why to shift the equilibrium towards the right? Because as we shift the equilibrium towards the right, so more of the acetic acid will be dissociated. So to dissociate the acetic acid completely, some of the heat is utilized here, and that is why the heat of neutralization for this reaction is less. So the reaction between acetic acid and NaOH, which gives sodium acetate and water. Here, if we write it in a ion form, the reaction between this H plus and OH minus, in this reaction the heat which is evolved, that is used to shift the equilibrium of this reaction towards the right, so that the acetic acid will dissociate completely, and that is why here the delta H, that means the heat of neutralization, is not equal to minus 57.1. It is the heat which is evolved here, the delta H here is less than that. For this above reaction, delta H is less than minus 57.1 here. The reason I have told you, some of the heat evolved during the reaction between H plus and OH minus is used to shift the equilibrium of the first reaction towards the right, so that all the acetic acid is dissociated. So this is how, therefore, the heat of the neutralization reaction for any of the weak acid and a strong base, or weak base and strong acid, will be less than minus 57.1. Now the next, that is the bond energy. Now what is the bond energy? The bond energy is nothing but the energy which is required to form a bond or break the bond. That is specifically called as the bond energy. Therefore, the bond energy is defined as the amount of energy which is either evolved or absorbed during the formation of 1 mole of bond from the gaseous atom, or it may also be defined as the amount of the energy released or absorbed to break 1 mole of bond into their gaseous atom, that is called as the bond energy. So I tell you the definition in the both ways again. The first definition, first way of definition, the bond energy is defined as the amount of energy or heat either evolved or absorbed during the formation of 1 mole of bond from their gaseous atom, that is called as the bond energy. This is the first way. Second way is, again, the bond energy is defined as the amount of energy either evolved or absorbed when 1 mole of bond are broken down into their gaseous atom, that is called as the bond energy. So for example, H2. So bond energy here will be one of this bond. If this is break or made from the two gaseous hydrogen, that is nothing but the bond energy. This is a simple diatomic molecule. So in case of the diatomic molecule, the bond energy is nothing but the bond dissociation energy. That means to break a single bond, or to make a single bond, that is nothing but the bond energy in case of the diatomic molecules. But for the polyatomic molecules like methane, here now four bonds are there. Four CH bonds are there. So how the bond energy will be? For each CH bond, the bond energies are different. They all are not same. That means these are their four bonds. So every of these bond hasn't same bond energy. The bond energy for this bond, for this bond, for this bond, and for this bond, they all are different. Therefore, the average of energy for all the bonds is taken as the bond energy. For every bond, they require the different bond dissociation energy. So, to define the bond energy for the molecule, the average of it is taken. Now, from the bond energies also, we can calculate the enthalpy of the reaction. The formula is delta H for the reaction is equal to the summation over bond energies of reactant minus summation of bond energies of product. So this is how we can calculate the delta H for the reaction. So from the values of bond energies, we can calculate the delta H, that means the enthalpy of the reaction, and the values of the bond energies of the reactants and the product, that can be taken from a standard data. The different bond energies are given in that data, and from that we can calculate the delta H, that for the reaction, the enthalpy of the reaction can be calculated. Let's take one example. In an example, we have given a reaction. This reaction we have given. And for this reaction, we have asked to calculate the enthalpy of the reaction. So here, we have given the bond energies for H2. Bond energy given is 435. For bromine, it is 192, and for HBr, it is 364 kilojoules. And we have asked to calculate the delta H for the reaction, that is the enthalpy for the reaction. So let's calculate it. For this, we'll directly use the formula, that is delta H for the reaction is equal to the summation of bond energies of the reactant minus bond energies of the product. Now here the reactants are hydrogen and bromine, and your product is hydrogen bromide. Therefore, delta H for the reaction is equal to bond energy of hydrogen plus bond energy of bromine minus bond energy of HBr. So let's just put the formulas. The difference, 335 plus 192 minus 364. So this is equal to 435 Here, this is twice 2 into binding energy because in the reaction it has formed twice. So 2 into binding energy of HBr. We have left it here. So this is how 627 minus 728. That means minus 101 kilojoule. This is the enthalpy of this reaction. So this is how from the bond energies we can calculate the enthalpy of the reaction. Next time we'll see the different heat like heat of solution, the heat of hydration, the heat of fusion, the heat of sublimation. These different types of the heat